Can you hear me? All right. Slides are also here. So, hello and welcome to my talk about trust minimized wallets. Like the session before, this is all about wallets. Doesn't matter what flavor, can be a mobile app or a browser extension. And it's also about wallet security. So some of you may use these hardware wallets like the little ledger devices. And they are great tools to protect your private key. You can securely sign transactions with them. But what they do not help you is to secure the wallet itself, like what it displays. The Ethereum balance, the tokens, and your account history here in the bottom. So to understand how this gets secured, we have to look at how the wallet obtains data, like how does it obtain the balance, for example. And the answer to that is Ethereum as a decentralized network. Every single Ethereum node has a full copy of all the account balances, all the transactions whatsoever. And if you catch one with a public RPC, like that's exposed, you can ask it for your balance, and it will comply and send you your balance. The issue here is the security, though. Like, this is all based on Trust Me Bro security. So if you connect to a malicious node, it can tell you a wrong balance, which can be a problem like for refund scams and whatsoever. So how to fix it is that some users, they decide to run their own nodes. Like they set up a Raspberry Pi at home and then configure their wallet to ask the Raspberry Pi. And because that one is running a full node, it can run the full validation and ensure that it only provides correct data. It's a bit of an issue, though, because you have now this extra box in your home. If you want it on your phone, then you are going to struggle because we are still having the requirement for like the 4-core CPU, which is possible on phones now, but you also need 16 gigs of RAM and 2 terabytes of disk, which is still a bit too much these days. So how to make it more convenient is the answer is go to the cloud. There are web3 API providers that have this capability as well. You can just connect to a server, ask them for your data, and they will send it to you. And the security here is a bit better because those companies have a reputation that they can lose if they are known to provide wrong data. But it's still a trusted relationship. I'm putting here this little glow on top of them. And if you look at this, it also means that all of this decentralized stuff on the right, it kind of becomes irrelevant for how the wallet operates. So this is also shown by the security features that are unlocked by the central provider, like the downtimes, like if they are down, your wallet doesn't work. If they get hacked, you're exposed to their security. They can also geo-block you, like if you're a resident of a country that they don't like, you don't have access to your wallet. And there's also this privacy problem that a lot of these providers start to have privacy policies where even if you segregate your funds across multiple ledger devices, that they still see that the same IP is asking about multiple wallets, and they likely belong to the same person if that keeps happening. But on the other end, there are also advantages, like it works on mobile. This is what we try to solve, and it's also very cheap to run. Like any wallet that we use is essentially free to use, right? So when we have this trade-off, downsides, upsides, usually the convenience wins, and over time, this also means that there is some consolidation happening, and these days, most wallets just rely on Infura or Alchemy to provide the correct data. So that's today's reality, and now the question is, how do we get better than that? And the answer to that starts with EIP 1186, ETH-GET proof, and it works by adding a correctness proof to the response. So this means that now the server provides the proof that the data itself is correct, and when we verify that, it makes this trust relationship disappear. We only rely on the server now for data availability because we can verify that it's not lying anymore. And because the server gives a proof, it also means that we can now ask any server for the data. And this is great for decentralization because we have a convenient system that works and that's also secure. To understand this proof on a technical level, we have to understand how Ethereum stores its data. All the account balances are stored in a tree structure. And your address, like the wallet address, can be used to identify where in this tree your balance is located. And there is something called the state root, which is like the root hash of this tree, a commitment to all of this data. And we want to be able to compute it to verify this proof. And for that, we have to understand how to compute all those intermediate nodes. And it's a Merkle-Patricia trie. The way how it works is for every inner node here, it's a hash over all the children. Like here we have a binary tree. The reality is a bit more complex. It's like multiple siblings that you need. But as long as you have all of the children, you can compute the next layer. So in order to obtain the state root, we need all the siblings, like these 3 elements, and then we don't need to send any of the rest, and we can compute the state root. State root is also part of the block, so if we compare it and it's the correct one, then we know that the data has to be valid. So problem shifts to how do we know the correct state root, right, that we are expecting. And that's from the beacon chain, like it's called the Altair Light Client Protocol. And every single block is signed since proof of stake. And there is a subset of validators called the sync committee. It's only 512 validators, so it's very compact to track all those public keys. And with that, we can check the signature and then know that the state root is correct, right? This is a BLS aggregate signature. If a supermajority of the 512 sync committee members sign the message, then we trust that it's right. And this chicken and egg problem, where how does the wallet know the public keys, is solved by just also having the next public key set as part of the response. So you only need like an initial one that's hard-coded, and then as long as you get like 1 message per day, you can follow all the sync committees. Each of them retains its duty for like 27 hours. So 1 message per day is enough to follow the chain and obtain all the correct state roots. All of this is a bit complex to put in every wallet. There are many wallets. So it's nice that there are also libraries that abstract that. So the wallet UI, it can use like its same ETH-GET balance to this library, and that one then does this light client stuff and the ETH-GET proof to add the security. So it's a universal API for the wallet. Instead of using Infura or Alchemy, ask your local purifier library, and that one can then use any upstream RPC in order to obtain the data, and it's also secure, like it's all verified. There's also a decentralized network called Portal Network, which aims to be a decentralized archive node, so you don't even need a central server. You can connect via a decentralized peer-to-peer network and obtain all the data as well. That solves it for the balance. Like we have a secure balance now, but our wallet also has our ERC20 tokens and also the history. So let's look at the tokens next. Token is a smart contract, and the smart contract, like ERC20, all of the tokens, they implement a shared interface, and there is a function where you can query the balance of a wallet, and in order to obtain the balance, we have to call it. There's a function called ethcall that we can send to the purifier, and it will do its magic. So let's look at the magic. Because this is code from the smart contract, we have to execute it in our local EVM. So the purifier comes with its own little execution engine. It's like a little CPU architecture where you can run the smart contract code, and then we can download the code and put it in there. And whenever, as part of this execution, we need access to some data from the state, we can also do like this eth get storage add to obtain the data. And because the state tree that we have seen before doesn't only contain all the balances, but also all the code and all the storage slots, we can use the same eth get proof infrastructure here and validate it with the same state root as before. That way we get a secure way to obtain token balances. This works for all NFTs as well, same process. One issue is that it's a little bit inefficient because we cannot know in advance what data we will need, so there are a lot of round trips involved. Like there are concepts called access lists, but they are best effort and don't always work very well. But at least we get the security. And once again, for a wallet, just add this web3 purifier library and use it the same as any upstream RPC today. That only leaves the history. And once again, ERC20 standard defines an event that's emitted on every token transfer. You can have, like in Solidity, up to 3 indexed values when you emit an event. And every time that an event is emitted, it generates something called a log. And there is always an entry for the address of the contract that generates it. Then you can have up to 4 topics. And the cool thing is that there is also an API called eth-get-logs, where you can look up all the logs that affect your wallet by just asking, like, because in the events, like your address is in here, right? So you can just ask for your wallet in any of the topics and you will get all the logs that affect you and you can display them. So problem here is we have these logs, how do we verify them, right? And the way how this works is that when we execute a transaction, there is something called a receipt that captures all the output of that execution of the transaction, and the logs are just a part of it. And then we can do the same thing as with the state tree and just validate it using the Altair Light client against the receipts route in the block header. It's very similar to the state route, but this one gets reset after every block, so it doesn't carry on like the state that's persistent. So that way we can validate the correctness of a receipt, but there is still a problem. When we do eth-get-logs, we can validate every single response that the server gives us, except the missing ones, right? If they just don't tell us about some logs, we have no way to know that. So how do we fix that? Comes down to this field that's called the logs bloom. So how does the logs bloom work? Is that it's a bit vector, 2048 bits. And for every single item that is indexed, like the address, the 4 topics, we set 3 bits based on some hash function. We do that for every indexed log value, and we get like 3 bits for everyone, and then we just union them, and this is our logs bloom. How is this useful? Let's look at a query. Let's say we look for our wallet address. We can do the same transformation and find out what 3 bits our address matches to. And then if all of these bits are also set in the logs bloom, then we know that there might be a match in the data. And here, indeed, that's the case. Like our wallet is actually here, the recipient of this particular log. So we see the bits match, so there has to be something in that block that might affect us. Let's ask about the different wallet that has different bits. Like it has a 1 here, which is not present in the logs bloom. So we know that for sure, as part of this logs bloom, there is no single item that went into it that set this particular bit, so we can skip this data. But there can also be false positives. Like here, we have a third wallet that we query, which sets these 3 bits. But we can see up here, for these 4 values, this was never put into this bitmap. So we can get some false positives, and then when we download the matching receipt and check it, then only then we find out that this was not actually about our wallet. So there is some inefficiency there. And this logs plume is also part of the block header. So we can also use the Altair Lite client to validate that it's correct. So how it would work is that you use the Altair Lite client to download all the block headers. You can do so both ways, like first sync forward and then go by parent hash. And then for every single block, you can check, is there something in this block that may affect our wallet? And if there is, then download all the receipts and then filter them based on the ones that you care about. There is an issue with this system that mainnet just grew very large. Right now we have about 1,000 of these indexed items that get put into a logs plume on every single block. And if each of them sets 3 bits, that's like 3,000 bits in a data structure that's only 2,048 bits wide. So there are a ton of false positives, and this mechanism that was useful in the beginning of Ethereum is no longer really useful. Let's look at the solution here, EIP 7745, that aims to improve this filtering capability. The way how this works, by the way, this is still ongoing work. You can comment on it, leave feedback still. This is not yet set in stone. The way how it works is that all the logs that are emitted are assigned a global index for each of the topics and for the address, and that just goes up with every single log that gets added, 1, 2, 3, 4, then 5, 6, 7, 8, 9, and so on. So every single thing gets put into an ordered indexed way. And we don't actually care about the stuff that's not indexed here, right? So get rid of the value for now. And then one of the problems in the past with the logs plume is 2,000 bits is not enough. So let's just make it bigger. This is like 4,000 rows times 2 to the 32. Lots of bits, so no more false positives. And now for every single log value, like contract address, this transfer the from and the to, there is a transformation to compute the row. So each of them gets assigned to a row. This is the same row for a really long time, regardless of the instance. So if you have a lot of logs that cover your wallet, they will all end up in the same row. And then there is also a column transform that allows us to find a coordinate in that map that corresponds to this particular log, like the index also goes in here. So every single log value leaves one mark in this matrix. And this filter map, because it's so big, is also shared across blocks. It's no more the case that every single block contains its own full filter map. That would be too much storage. So how do we query this filter map? Is when we have a log value as a query, we compute a row from it. That can be done on the client side. And then we know what row we need to download. It's only a single one. And now there are these 2 marks in here. How do we know which of them correspond to logs that may be relevant? And that can be done by looking at this column transform. There is a way how it's created to reverse the operation. Like, as long as a mark was created by the same log value that you are asking about, you will get back the same index. For example, here, the contract address, let's say this left one is the contract address number 1, but we are asking about our wallet address, right? So this first one will not decode to a valid index because we are querying with an incorrect log value. But the second one, which is our wallet address. We can decode that because our query is the same log value as the one that was used to compute this mark. So once more, we have our query, we know the row that it pertains to. We download all the filter maps, the same row. That's a very efficient proof because it's always the same entry. And then we go through all the marks in there and see which one of them can we decode. Like for which one of them can we go back from the colon to a global index. This is very powerful. Now we have an efficient way to go from a log value all the way back to the index. And the false positives are fixed by resetting this filter map every 2 to the 16 marks. So that's like the upper bound, how many false positives we can have, because there can only be so many marks in a map. And it's also like 4 million marks that can be efficiently filtered with just one query because they all share the same row. So there is one more missing piece here. We know that number 4 is interesting for our wallet, but how do we know what logs corresponds to number 4? And for that, in EIP 7745, there is also a second data structure that is maintained, and that's called a log entry. It's essentially taking a hash over the log data itself and also position information about what block was it in, what transaction originated this log, if there are multiple emits in a transaction, which one of them was it. So with that, we can verify when we get the log later where it was and can cross-check it. And also, because usually when you start up a wallet, it knows how far it has synced, and you just care about information since your last time. Otherwise, you have to start from Genesis every time. Every time that there is a new block, there is also a log entry for that. And with that, we have a linear list that orders all the logs. If we do a range query between two blocks, the server can just prove this is the block delimiter, the first one. This is the end, so you know the exact range of maps that could affect you. You download the rows in those maps that could be relevant for your wallet. And that way, with just like 1 megabyte of data that you have to download, you can get all the logs that affect your wallet for the entire history of Ethereum so far. This is implemented in Go Ethereum as well. Like there is a branch from Scholt that does all of this. So this gives us a secure way to verify the logs for both correctness and completion. There is one detail that's still missing, which is for the ETH balance itself. The ETH balance is not a smart contract, it's just the native ETH token. So when it's sent, because there is no code that's run, there is also no transfer log for it. And there is another EIP to just have it do that. Like whenever ETH is transferred, just treat it the same as any other ERC20, except instead of a contract address, we just put a magic value here for the system address. But in the end, it behaves the same. This is important for smart contract wallets that transfer ETH, because like otherwise you may miss those logs. Like you send something from that wallet, you don't have a log, then your history doesn't add up to your balance. With this, complete history for users, and then likewise for validator operators that run their own nodes and stake. There is a similar problem that the rewards that you get for staking are currently not part of the logs. So this is another EIP to just add logs for priority rewards and also the withdrawals that you get. like in a new field. And with that, we can verify the entire data that's displayed in the wallet, the balance, the tokens, and also the history. There is still more missing, like when you click around in the wallet, maybe you want to see the transaction details. Those are covered by other EIPs that I won't talk about today. But all of this is available as a DevNet, like where you can play with. It's based on Nimbus and Ethereum.js. There is also the web3 purifier from A16z/Helios. And we have resources for developers like those efficiency EIPs that I mentioned before, the kurtosis config, and also guides for building your own purifier or your own wallet. Link is over there. All right, that's it for this session. If there are any questions, please right now. Yes?
For regular incoming transfers, like which is just an Ethereum transfer, how can you get the transaction history?
For an incoming transfer. Incoming ETH transfer. That's this EIP here, 7708. This one means that whenever there is an incoming ETH transfer, then your wallet is here in this 2 address, right? And because it now emits a log, we can use this, the filtering mechanism from before. Like you just query for your own address, and here your address is still part of this map, right? Okay, next question.
Isn't it heavy to query such a, like if at all I have a history of transacting from 2015, now I want that history in a wallet, I just registered. So I have to query from block maybe 100 to today 5 million.
Yes, that's fine. That's about 1 megabyte of data that you only need. Like if you know like what is your query, you can deduce like what row you need. It's only 1 row in this filter. And by the way, these filters also work on the existing implementations. There is just no commitment on chain today. But if you use Go Ethereum, they use this mechanism to accelerate the answers. So if you ask them ETH-get logs, all of it, it's very fast, like seconds for the entire history, about 1 megabyte of data. Any more questions? All right. Thanks for coming here. And if you use wallets, please tell them purified web3. They can use it like every other RPC, but they get a secure response from this. Like there is nothing else they have to change. And also Portal network for this decentralized archive node instead of a centralized server. All right. Thank you.